This is going to be the summary over Chapter 8, and we'll start going over the first few sections here of the chapter. So you got three major categories of radiation detectors. You've got gas, you've got solid, and you've got liquid. So three phases of matter. You can think of it that way. For gas, you're looking at ionization chambers, proportional counters, and Geiger-Muller counters or GM counters. Solid state, you've got TLDs, you've got OSLDs, you've got film, diodes, MOSFETs, and polymer gel. For liquid detectors, you've got calorimeters, and you've got chemical detectors. Phantoms are classified by shape and composition. They can be geometrical, in other words, spherical or perhaps a square, rectangle, or they can be anthropomorphic or more human-like. Composition, elemental, and electron density. Tissue equivalence, the same properties as tissue with respect to radiation absorption and scattering, and depends on the type and energy of radiation. You've got effective atomic number. So it's the effective atomic number of a compound or mixture that describes radiation absorption and scattering over a range in energy. You've got gas ionization detectors or cavity ionization chambers. These are characterized by their shape, collecting volume, and the thickness and composition of their walls. These instruments are used for a wide variety of applications. The larger the volume, the more sensitive the instrument, but the poorer the spatial resolution. Large volume ionization chambers are used for survey meters. So you've got thimble chambers shaped like a thimble, farmer chamber or mini chambers for beam scanning, survey meter chambers, things of that sort. External beam calibration carried out with a farmer chamber. You've got plane parallel chambers, also called a pancake or a flat cavity. They're used for electron beam measurements or measurements in the X-ray buildup region. And you've got well chambers. Well chambers are used to assay radioactive sources in nuclear medicine or brachytherapy. You've got an electrometer, which is connected to the ion chamber with a triaxial cable, and it provides a bias voltage across electrodes, measures the charge collected from ion chambers, calibrated by the ADCL. This is an agency or establishment put together to make sure that things are calibrated correctly. I forget exactly what that stands for, but we'll look it up in the chapter. Now, just because you have an ion chamber reading doesn't necessarily mean that's what you go with. If you are wanting an accurate beam calibration, you're going to have to take whatever your raw reading is, and you're going to have to multiply it by several different factors. You've got temperature and pressure correction. Ions may recombine as they drift into the collecting electrode. So you've got a recombination factor that you have to put into this. You've got an electrometer correction, and you've got polarization. When bias voltage is high, ions liberated by radiation are accelerated towards the collecting electrode. They in turn produce new ions, get pulse and individual count. So the gas multiplication here is something you have to consider. Proportional counters, gas amplification up to 10 to the 6th. Signal is proportional to the original charge produced by radiation. Your GM counters are designed for maximum gas amplification, operates at higher voltages than proportional counter. High voltage causes avalanche ionization, leading to large pulse of current. All pulses have the same amplitude, so you can't discriminate with the energy. And it's good for locating radioactive contamination or finding lost radioactive sources should you ever be in that bad of a situation. And here you've got a graph that summarizes the behavior of gas ionization detectors. At low applied voltage, there's a great deal of recombination, so that's why they call it the recombination range. At higher voltages, saturation is reached. It is in this region that ionization chambers are operated. As the voltage increases, further ion multiplication occurs and the signal becomes proportional to the original charge produced by the radiation. This is the regime of the proportional counter. At still higher voltages, avalanche ionization occurs. And we reach the conditions under which GM tube is operated. And if it increases further, then spontaneous discharge or a spark occurs. This diagram shouldn't be taken too literally. There's no single instrument that can operate in all of these regimes. Each regime requires individual design characterizations. So in other words, this is the kind of thing that you see going on whenever the voltage is applied and you have certain things that go on with ions, and you need a device for the specific area for the specific purpose you're looking for. TLDs are, and you've seen these most likely, they're solid state dosimeters used for in vivo dose verification, skin dose, that kind of thing, and for personal radiation monitoring. Optically stimulated luminescent detectors, or OSLDs. No wonder they have an abbreviation for it. A small fraction of the absorbed dose is stored in a crystal structure, and when it's illuminated, some of the stored energy is released in the form of light. And OSLDs can be reread, unlike TLDs, where it's sort of a one and done kind of thing. Film. The degree to which film is darkened is related to the dose received by the film. You've got an optical density calculation here, which is a measure of film blackening when you've got an incident intensity and then you have a transmitted intensity. The usable range of the optical density extends up to about 2. You have base plus fog. So the optical density of a piece of film has not been exposed to any radiation. Typical value is somewhere around 2. You have advantages, disadvantages, and then you have radiochromic film, which is not based on silver halide. It has no energy dependence. It's self-developing and insensitive to ambient light. Then you have diodes. These are small solid-state devices that produce a small current when irradiated, even in the absence of external bias. They're very sensitive and give a real-time readout, frequently used for patient dosimetry. MOSFETs, again, we'll look at the what that stands for here in the chapter. Small solid-state transistors, threshold voltage shift is proportional to radiation dose, used for patient dosimetry, lifetime of about 200 gray or less. You've got polymer gels. They have the unique capacity of measuring the 3D dose distribution read by either MRI or optical CT. Calorimeter, insulated container that can be used to measure the small temperature rise associated with absorbed dose. Chemical dosimetry is based on metallic ions in an aqueous solution. Tissue equivalent requires large doses. Measure dose in liquid of complex shape requires spectrophotometer to measure change in optical properties of solution. And survey meters, portable radiation detection devices that are designed to protect the presence of radiation and to make a rough measurement of the radiation level. And then you've got a little bit right there. Here, this is kind of interesting. A neutron survey meter, an Anderson-Braun type proportional counter with bromide fluorine gas at the center of polystyrene cylinder. Moderates neutrons. Neutrons interact with boron 10. So let's go back to the introduction here. A lot going on in this chapter. So the last chapter, we discussed concepts and defined quantities that could be used for radiation measurement, like exposure, absorbed dose, and dose in free space. So here we're going to discuss how you can use certain devices to detect or measure the radiation. And in chapter 11, we'll discuss how measurements of radiation beams made with instruments discussed in this chapter can be used to calibrate these beams based on absorbed water, or absorbed dose in water. So you can categorize radiation measurement instruments in terms of the type of radiation measurement they're designed for and the type of medium used for detection or measurement. So in radiation therapy, you've got four main applications of radiation instruments. You've got radiation machine calibration, you've got survey work, you've got personnel monitoring, and in vivo patient measurements. Calibration requires very accurate measurement of the amount of radiation emitted by a radiation producing device, a linear accelerator. Calibration instruments need to be very accurate, but they don't need to be very sensitive because of the level of radiation is high. Survey meters are used to detect and provide a rough measure of radiation levels in the environment. They're used for detecting and locating radiation contamination. Survey meters need to be very sensitive, but don't need to be highly accurate. You know, we're just looking to see if something's there, not necessarily how much of it is there. Both calibration instruments and survey instruments need to provide measurements of instantaneous radiation levels. Personnel monitoring devices are used to track the amount of radiation that individual radiation workers receive. They need to be sensitive because they are required to measure small amounts of radiation. And they need to measure cumulative radiation exposure. In vivo radiation detectors are used to monitor the amount of radiation the patients receive during treatment. So each one of these types of devices have different attributes because we use them for different types of situations. So again, you've got three major categories of radiation detectors classified according to the phase of the medium: gas, liquid, or solid. The medium used for detection may not be the same as the medium in which the radiation is measured. For example, a gas ionization detector may be placed in a solid medium to measure the radiation in a solid. All of the various types of gas detectors are based on the ability of radiation to produce ionization in the gas. The solid and liquid detectors employ a variety of mechanisms to detect and measure radiation. So the major types are gas, and within gas, you've got ionization chambers, proportional counters, and Geiger-Müller counters. Solids, solid state detectors, TLDs, OSLDs, film, diodes, MOSFETs, polymer gel, and scintillation. And liquid dosimeters, you've got calorimeters and chemical dosimeters. So the design of an individual radiation measurement instrument depends on the intended application and on the medium used for radiation detection. Each of these detector types are going to be discussed here. So I'm going to go ahead and end this video, and then we'll pick up with 8.2.